Welcome to the session. My name is Riadh Ghaddab. I'm from Baylibre, and today I'm going to present the ZMS, the new storage system, the lightweight storage system in Zephyr. So let's go ahead and see our agenda for today. After a brief introduction and some background history about flash technology, we're going to see the reasons why we designed the new storage system in Zephyr. Then we move to the most important part, how does it work? We're going to go into details a little bit, from highlight, of course, high level. And then we're going to talk about ZMS and settings, how do they work together. If we have time, we're going to go into the how to get the best performance section, and then some upcoming features. And then, of course, the question and answer session. Okay, so a little bit of introduction. So about Baylibre. Baylibre is an open source consultancy company specialized in everything that is embedded from like Linux kernel, U-boot, Yocto, Zephyr, AOSP, everything related to embedded systems. You can check the blog page for more information about our contributions. And it's based in Nice, in France, but we have remote workers in all over the place in USA, Canada, and everyone. So about me, I joined Baylibre in 2017. I worked in all of those fields, AOSP, Zephyr, Yocto, Linux kernel, but most recently I'm a contributor now in the Flash subsystem in Zephyr and a maintainer of the ZMS storage system in Zephyr. So let's go ahead and see, let's have a look at some background history about the Flash technology. So a lot of you know already about the classical NOR Flash technology, which is used in almost all the devices. It is made of floating gate transistors. It has limited write endurance, like 100,000 write during its life cycle. But the main important feature, characteristic, is that it needs to be erased in a page, in erase unit, what we call. Sometimes people call them a page erase, before being written. So before we write them in words, we need to erase a page. The new technologies, however, like the RRAM, the one in the bottom, RRAM and MRAM, which are made in a different technology, you can see the details online. The main characteristic is that they do not need this erase operation before being written. Everything is taken care of in the hardware, so we can write them directly in words. We don't need to erase any pages. And for these new technologies, that's why we start to think about making a new storage system. And you can see also this is for future. They have higher write endurance, they have low cost, low power, and everything else. So it's they can be also have higher density than the classical NOR Flash. So about the existing storage system, now let's talk about what exists and how, if they can support the new technologies or not. So the file system these are some of the file systems that exist in Zephyr. The little fs is a full file system, actually. It's not a key value storage system, and also designed mainly for the NOR classical Flash. So it means that from its operation, it needs to do erase before writing words. The Flash circular buffer is more complex to understand by developers or used by developers. It's not used a lot, and also it has a significant overhead to the wear leveling algorithm. We're going to see later what is wear leveling for ZMS. The NVS looks like ZMS. It's a key value, also storage, lightweight, but the problem is also it needs an erase. So the NVS needs to erase a sector before writing into it. And it's designed basically for the NOR Flash. And also it has a limited set of supported IDs like 64K. And of course, it's not for 64K IDs, it's not scalable for large density Flash devices. So why did we design a new storage system? So first of all, like I said, we need to design a storage system that is compatible with all types of Flash technologies, not only the classical Flash, but also the new ones like the RRAM and MRAM. And one of the problems is the erase. Like I said, if for the classical Flash devices, they are erased in a page, so it's one operation for 4K of memory. But for the new devices, if we want to use the old storage systems that exist today in Zephyr, we need to emulate those erase operation and do, for example, for 4K, if the unit that we use is 4 bytes to write, we need to make 1K write operation to make the same status. So this is an overkill for the new type of, devices like RRAM and MRAM. So we need a storage system that manage the wear leveling of this type of devices. Means that all the memory cells needs to be written in. They need to have the same write cycle in all the time. We also need some support for CRC built-in verification for data integrity. We need to have larger number of IDs, not like NVS, which has like 64K. This time we designed it so that it has 32 bits, so it's like 4 billion. So it's scalable for larger storage memory. It should be also power loss resilient, and it's also we designed it to be optimized with the setting subsystem. So the setting subsystem, we're gonna see it later in the next slides. So for all these reasons, to meet all these requirements, we decided to make a new storage system called ZMS, the Zephyr Memory Storage. So let's go and dive in and see how does it work. So I'm not gonna talk into details on what is this API. The API is quite simple. It's like any API for a storage system. It has a read, write, delete, mount before use, and clear after use. The most important part is that because it's a key, like I said, it's a key value storage system, you have an ID. So each data is related to a unique ID. And the ID here is, like I said, it's 32 bits. So we have like 4 billion entries that can be stored in ZMS. You can also, I put the links there, okay, for people that wants to see the details about what these functions does and some helpers for some applications. You can have a look at them when you see the slides later. So to understand how it works, first thing, let's see how it divides the memory, how the memory layout looks using ZMS. So in ZMS, the memory is divided into units called sectors. That's the first information. Second, so for devices that needs arrays, like I said, the classical flash, the unit, generally, the sector size is equal to the arrays unit. Sometimes it's called also the pages. People know them by pages, not arrays unit. But actually, they are the arrays unit of the device. And commonly, they are like almost 4K, but it can also be multiple of these arrays units. So the sector size can be like 16K, for example. But for non-erasable, the devices that do not need arrays, do not require an arrays, that could be any, the sector size could be any value that is multiple of the write block unit. The write block unit is the smallest unit that you can write into a device. For some devices, it's 16 bytes, for others, like 4 bytes. So we don't have a constraint of the page or the arrays unit. In ZMS, these are the main information. I'm going to show the details later. One sector should be always empty. This is for compatibility with the flash, classical flash devices. One sector is always open. That's the sector that we write in it. And all the other sectors are closed. So let's see an example. I think a picture is better to understand what's going on. So let's see an example of a memory of partition of 16K. We have 4 units of this memory partition divided into 4K. So at the beginning, no sector is used. So all the sectors are open. We didn't use anything. The first thing that we do, the ZMS needs to erase the sector that is next to the one that we're going to write. So the sector 2 is erased. We're going to see later how it's erased. But the sector 2 is erased, and we start filling all the data in sector 1. Okay? After a while, sector 1 it becomes full, so we close it, we open sector 2, and we erase sector 3. We do the same thing with the sector 3, so we close sector 1 and 2. Sector 3 is now open, sector 4 is erased, and we go on until we wrap around to sector 1. So it's all the operation like it's what we call here a fast-forward write. We only write one time a memory cell and we advance. We never return back. With this feature, all the memory cells are going to be written equally at the end of each cycle. So we know that, at any time, all the memory cells have been used equally. That's called wear leveling, okay? And that's how we maintain the lifetime of the device. But we have, like I said, we have an erase. I didn't show you how to erase the sectors, because for classical flash, the sector that is erased is like FFF, or the opposite for some type of devices, or zeros. But For the classical flash devices, there are only one operation that erase, that we get this status in one operation. We cannot do the same thing with RRAM and MRAM. So how do we do it? Because if we do the same thing with the classical flash, we do multiple writes, we're gonna overkill the device. And to understand how we do it, let's get first a little bit of detail about what is the sector layout. So this is only one unit of what I showed before. The sector layout is simple. The data is written from top to bottom, and the metadata, also what we call the ATEs, that's a very important term, ATEs, because I'm gonna talk a lot about ATEs later. This is the allocation table entry is written from bottom to top. So it's each metadata, it has information about where the data is. So it's metadata that is useful for operations. And we need also some header ATEs. So each sector have at least two. Here I call them the empty ATE and the closed ATE. And we're going to see later we have also the garbage collection done ATE, which is another ATE that is used when we finish the garbage collection. Just there's a mark for the garbage collection that it has finished. So the most important part, like I said, is the headers. So the header ATE, we have them both, the empty ATE and the closed ATE. So the most important part is that the empty ATE, which is the bottom of the sector, is only written when we erase a sector. I'm going to show you how to erase a sector later. And then the closed ATE is written only when we close the sector, and the garbage collection, of course, is a marker after finishing the garbage collection, and all the ATEs, that's the most important part, has a cycle counter. So the cycle counter that is in the ATEs, it is what I represented here, but it's the same, let's say it's the same structure. So the closed ATE has inside it, for example, a cycle counter here of value 1. And we use that information. First, it has a meaning, why we call it a cycle counter, because it represents the number of times that sector has been written. So if we have like sector cycle 2, it means that we wrapped around 2 times. If it has 100, it means that we wrapped around 100 times. And the most simple one to understand is the closed ATE. So a closed sector has the cycle counter of the empty ATE and the closed ATE the same value. So that's what we represent by, we represent how we represent the closed sector. An open sector has the empty ATE cycle counter that is value of the closed sector plus 1, okay? And the erased ATE, the erased sector, sorry, has the cycle counter of the ATE, the empty ATE, which is also plus 1. So it's like an empty, an open sector, but we're gonna see later why this is considered as an erased sector. So the open and erased looks like, not like the closed sector, but we're gonna see why. So here we're gonna see the representation of these three type of sectors, but in with the data and the metadata. So you're gonna see here that for the closed sector, all the cycle counter for all the ATEs, the header ATE and all the ATEs have the same value. Here it's 2, which means that the cycle counter of the ATE is an indication if they are valid in that sector. If they have the same value as the empty ATE, it means, okay, these are valid allocation table entries, and we consider them, and because these have the same value, it's a closed sector. An open sector, you're gonna see that the empty ATE has the cycle counter 2. These have the same cycle counter as the empty ATE, which means they are valid, but okay, it's an open because they have different values. But the erased sector, if you see here, the difference is that the cycle counter is 3, so it means that the only newly written entity in all the sector is the empty ATE, which has a cycle counter that is different than all the others. So in this way, we consider that all these ATEs are non-valid, so it means that as if there is nothing really written in the sector and it's empty. And when do we do the erase operation? It's after a garbage collection. Here it's a little bit of detail, but let's see how these are a little bit of detail of how the garbage collection of ZMS works. It's a little bit detailed, but we're going to see it's simple to understand. So we have an open sector on the left, a erased sector on the middle, and the right, the closed sector. The first thing that we do, we're going to start filling all the data in the sector 1. Okay, now it's full. The first thing that we do is that we close it. So if you see here, let me go again. So here the cycles are different, but when we close it, we only write the close ATE, we give it the same value as the empty, so now it's closed. This means this is a full sector. The next thing that we do is that we open this one. It means we move to the next sector. It's already, we don't write anything because it is already empty. We move to the next sector, but before moving this, we need to garbage collect all the data that is here. What we do is that we're gonna copy only the unique, like I say here, the unique IDs that are in this sector into the open sector. What does it mean, the unique IDs? It means that we only copy data that is useful, that has not been overwritten in most recent sectors. The most recent sector, for example, here are sector 3 and 2. Okay, these are the most recent sectors. So if data is in sector 1 has been overwritten in sector 2 or 3 with the same ID, we don't need to copy it again in the open sector. But if a data is old and has never been overwritten, we need to keep it. So we copy it into this sector. Of course, when copying it, you see it gets the same cycle counter of the empty AT here. And we go on after copying it. We need, of course, the marker that, okay, it has finished the garbage collection. And how do we erase the sector? We just modify the cycle counter of the empty AT and we consider that this AT is erased. So the operation is quite simple, as you see. So let's see, some of the features that were introduced by ZMS. So one of the features is that it has 32 bits ID, so it's like 4 billion combination of how many entries that you can write in ZMS. It has also 64 bits address space. If you divide, in fact, if you take the lowest part of the 64 bits, you can define the sector size of your partition, yeah, and the sector number. If you want 100 sectors, and I don't know how many the size of the sector size. So they're divided into 2 parts. So you can have a 64-bit address using this combination. It has also predictable device lifetime calculation. The details are all online. So if you want to know how to calculate those numbers, you can see them online. And if you have some question, you can ask me. Also, one of the features is that for small data sets, so if you have a data that is less than 8 bytes, the data actually is written in the metadata itself. So we don't do two times the write to write the data. It's only one write operation to write a small data size. But for larger, of course, we need to make 2 writes. And also it has a built-in CRC for data integrity. So if something goes wrong, you get an error. Okay. So after we went through all the features of ZMS, like I said, everything is documented online in the documentation, but if you have questions, don't hesitate. Let's see how ZMS and settings actually work. So why settings and what is settings first? So settings is an old subsystem introduced in Zephyr in 2018. And it's basically designed to provide capabilities for to write the application settings. And so mainly, let's say, to resume, the difference is that settings settings is implemented on top of all the other storage systems that I listed. Like settings is on top of little fs, on top of NVS, on top of FCB. So it's a higher level subsystem, and why is it used? Because it's simple for developers sometimes to use path names. Like I said here, it's like namespace. So it's simpler for developers to store keys, for example, key 0, key 1. They are more used, or maybe they had older code, I don't know, that they use. It's the keys are, for example, related to paths, so to root path. So like, for example, here it's the key 0 is stored in ITS/key 0 and key 1 is stored in ITS/key 1. So we need a system that manage the these strings. And with, for example, setting subsystem, for example, all the keys can be loaded. That's why developers use it, because when you only provide the root of the path, you can load all the keys. That's why mainly it's used. So it's very easy for developers familiar with the file system trees. So like I said previously, settings is on top of all those storage systems. And to make settings work with ZMS, we need an intermediate layer called ZMS backend. The backend has been added recently in Zephyr in February 2025. So you can see that the user application either can use settings, and then it goes, and settings use ZMS, and ZMS use the Flash API, or the user application also can use ZMS directly. The user application, of course, can use the Flash API directly, but it's going to harm the device and kill the memory cells in the device. So it's not recommended to use the Flash API directly. So, like I said, we added ZMS backend, but what's different in ZMS backend than the other ones? So we noticed that there is the settings load, which is, like I said, is the operation of loading all the keys from a certain path, is very slow. Basically, because the settings subsystem, it's really it's a blind subsystem, because it searches. For example, if you have 100 settings, settings subsystem will store them in an incremental ID way. So if they store them, the settings subsystem store all the paths from for example, from 1 to 100. And when you look for a certain key, it must first search through all the 100 paths to find what is the ID that corresponds to that path before reading that ID from ZMS or NVS or any other lightweight storage system. And also, like I said, once the ID of the path is found, it starts retrieving its data, and it adds a huge latency for application that has a huge set of parameters. So what is the solution with the ZMS backend? Basically, we added a hash function. The hash function, what it does is that it takes the path, it hashes the path into an ID, because now we have 32 bits ID, so it hashes the path into a 32-bit ID. It makes a direct connection between the path and the ID, and it looks for the data from that hash ID. So for example, if you have like this key, you hash it, you get an ID, and then with that ID, you have a direct path. So the settings subsystem doesn't need to iterate over all the parameters, all the paths that it has stored to find your path, but it's directly now with the hash function, it's getting the ID and searching for the data. Of course, there could be some collisions between hash values, but they are also handled as well. We added also in ZMS backend, that wasn't before, we added a function called settings load one. Before it was like loading, like I said, from a root path. So it was loading, the settings subsystem was loading all the keys, or if you have one key, it was loading only that key. But we added a settings load one operation in settings because of the hash. Like I said, we have a direct connection between the IDs and the path. We can, for application that needs only, for example, to get one value given a certain path, you can use that function to get that value faster. Like I said, it's faster with ZMS. Then the problem is how to load them all with ZMS, how to load all the IDs, all the settings elements using ZMS backend. Because settings, how settings before that was loading all the keys, it's just going to iterate from 100, for example, from 1 to 100, because it's like an incremental ID. It runs from 1 to 100 and loads all the keys. But how do we use it now in ZMS? Because we don't have incremental IDs, we have hashes. So hashes are really variable. So they're different one from the other. So we added a linked list that maintains the link between all the hashes. And to load all the stored elements, of course, we parse all the linked list to get all the elements. And also all the other functions, so settings load or settings load subtree works with ZMS backend. So let's see if we have, at least I think we have 5 minutes. We can go fast with this section. So a lot of people ask me, I mean, they have very huge latency and they ask me how to increase the performance, ZMS or ZMS with settings as well. So how to increase the performance, that's a very important part when using ZMS. And a lot of people, they don't know how to optimize this performance, even if it is already written in the documentation. The sector size and the sector count are very important parameters to take into account when using ZMS or when designing your application, because it depends on how much data are you going to store with your application. It depends on how often your application is also going to is going to store data, and also what is the maximum latency that is acceptable by your application, because you have a latency, for example, with the garbage collection. Let's say the entry that you're gonna write, and that entry that's gonna trigger the garbage collection, the latency is gonna be the biggest one. So what is the maximum latency that your application should accept? And like I explained here, for example, the more sector you have, the faster the garbage collection will be for the same memory space. The less sector you have bigger sector size, which means the garbage collection operation is going to be slower. And like I said, the size should be twice the effective size of data that can be stored in the sector. The effective size is also explained in the documentation online. How to compute that, everything is explained in the link that I put there. Also, if you have like a small data size, it's faster, because like I said, it only need one write operation instead of two. So if that's important to understand. And also we have some cache mechanism in ZMS. The way to dimension also the cache is very important, because it depends on how much RAM are you going to use. So each entry adds 8 bytes. Of course, the optimal case of cache size is to have as much number of cache entries as much as data that is going to be written. Also, if you use settings load 1 is very fast compared to loading all the settings, and there's also a cache in the settings. So I made a little bit of an example to understand it better. Okay, we understand things better when we have an example here. So I tried, I just edited a little bit the performance test, which is also upstream. And I took the first case. The first case is the case where you design the application. You said, okay, I'm gonna need 60 settings entry, and the memory size that I'm gonna choose is 2 sectors of 4Ks. This is almost full. So this is almost the maximum capacity, the minimum capacity that you define in your partition to be able to store those entities. Like I said, if you choose 2 sectors of 4K, actually you're only using 4K because 4K, the other sector should be always erased. Like I said, in ZMS, 1 sector is erased and the other sector will be open. So you only use 4Ks and it's almost full. If you see the numbers that I get here, when it's almost, because the garbage collection operation is doing this all the time when you run it like 50 times. People generally, when they use the performances, they run it one time, they get a number, and okay, I have 1 second or 2 seconds, so it's good. But if you run it multiple times, when you wrap around, that's when you get the real numbers with all these storage systems. When you wrap around all the sectors, means all your sectors are closed, and then you wrap around and you start looking at the real numbers. Then that's when you get the real numbers. So if you see here, you have, for example, with NVS, because it's like I said, it's doing the arrays on top of ZMS. On the arrays operation is doing like 1,000 writes, so that's why it's slower. It's like 40 seconds. With ZMS, it's also very slow. It's like 21 seconds for 60 entries 50 times. So it's also very, very, very slow. But let's look at the case 2. So we increase the partition size to the double. To the double. So we have like 16K now. So it means that we have theoretically 3 sectors that we can use of 12K, and we do the same test, we didn't change anything, the same test, okay? Now we go down to 3 seconds. The same test runs in 3 seconds instead of 20 seconds. Also, like I said, for garbage collection operation, you can see here the entry max. It means one of the entries or multiple entries, the maximum latency time was 150. That's because during the garbage collection operation, it lasted 150 milliseconds. Okay, but the average of the other units is like 1 millisecond. That's the average. We modified a little bit, like I said, the same memory. So before it was like 4 sectors of 4K. Now it's 16 sectors of 1K. Okay, it's the same memory space. What's different now, it's a little bit slower. It's 3.9, but it's acceptable. But the difference is that the maximum, like I said, the garbage collection now is faster. So the maximum latency that you can get with one entry is 50 seconds. So depending on your application, you need to know how to modify these parameters to get the numbers that is acceptable for your application. Now I started using a little bit of cache, of ZMS cache. I just, for example, added 16 lines of cache, and it's a little bit better. Now it's 3.1 seconds. Before it was, like I said here, 3.3. Now it's 3.1. I used also the cache for settings. I enabled it's a special hash function for ZMS for settings. It goes down to 2.1, and then if I increase the cache size, it goes to 1.2. So can you imagine? I mean, going down from 20 seconds to 1.2, and also there are a lot of other parameters that you can use. They are documented online that you can use to optimize the performance of your application. So I'll go a little bit quick on this one. We are out of time. The upcoming features, these are features that some of them are already almost ready, and some of them are just ideas. So the cycle counter, we're going to add an API to retrieve that from the storage, because that's an important information. People developing application, they want to know how much, what is the life cycle of their device, if it's going to die soon or if it has still some years to go. So it's an important information to get from ZMS. And we have that through the cycle counter, so it's important to add an API to retrieve it. So the pull request is almost ready. We're going to push it very soon. Also to add the 64 bits ID support. Some subsystems also need even larger set of IDs. So the pull request is already under review. It's going to be merged very soon upstream. And also one of the ideas is to add multiple format ITEs, which means that we can in ZMS add the support of not only one type of metadata, but you can support 32 bits, 64 bits, or maybe, I don't know, some application if they need 128 bits and different format of ATEs. We can add the support of this in the future if we have enough time. So also one of the upcoming feature is that we add the recovery function when something goes bad into the memory, or we have a memory region that is dead, to retrieve the ZMS entries. And also one important thing, that's the last thing, I promise, to add a helper function, because a lot of people ask me how to compute even if it's documented online, a lot of people do not know how to compute the recommended memory size for an application. So I think we're going to add a helper that will compute automatically what is the necessary memory partition that you need to configure to get the best performance in ZMS based on how much entries are you going to store and how often, right? So thank you very much for your attention. I hope that you liked the presentation. And do you have any questions? Go ahead.
Back with the updating of the closed and open ATEs for the legacy flash devices, how do you update a closed or open ATE when you need to erase the page to write it first?
Go ahead. Which one? This one?
Yeah,
Yeah, this one.
So
Mm-hmm.
You update that close ATE to cycle 3.
Mm-hmm.
How do you do that when the page needs to be erased before you can write to it?
How do I do it before the page? How do I close the sector?
Yeah.
Or the cycle counter, like you have to update.
Yeah,
You
exactly.
cannot update in no flash. You have to erase and then write. So how? Because I had the same question as you.
Yes. So for the flash, the classical flash, there is an additional operation. So the additional operation that we erase. So to erase the classical flash, that's where we only do it for the classical flash. We also do call an erase operation. So they are erased, and then we write, for example, the empty ATE to erase it. Okay. So it's like there is an additional step with the classical flash. We need to erase them.
Okay, great. So this shows the situation for RRAM or MRAM. For classical flash, the closed ATE will not be there. And it's only written when you actually close it. Am I right?
Yes. So So your point of view is that when you erase it, there is no closed ATE, right? That's your question.
All the data disappears.
Yeah. So the data disappear. For ZMS, anything
Going from open to close is the question here. So you've got on open,
going from open
open to close. So on
to
here-
close. This one, right?
So it's just that cycle is changing.
Exactly. So here we don't erase. A closed sector doesn't mean it's erased. A closed sector, it means it is full.
But
But how do you update the
how do you
cycle
update it?
value from 1 to 2 without erasing on a NOR flash? If I have a 1 number written in NOR flash and now I need to convert it into a 2, I can't do that, right?
Yes. So this sector before being closed, before even being open, has been erased in the previous cycle, and that part of the memory we don't touch it. Okay. So in Flash, it's never been written during the cycle of data. It's only that part of the data that has been erased before. We only write it when we close the sector.
So it's not actually one, it's an implicit one.
Exactly. For this is the value 1 for, like I said, for RRAM, MRAM, because they are not erased, but it's an implicit. Actually, the reality, it's just like I said here. The presentation is just to simplify how the user will see it. But actually, we don't care about the value that is in the close ATE as long as it is different. Actually, the main thing is that we should make sure that it's the empty ATE cycle is different from the one in the close ATE. So if there is nothing there, it's an open sector.
So it doesn't have to be 1 plus 1 plus.
No, actually, but that's a simplification, like I said, because I cannot go through all the types of flash memory here, the RRAM and MRAM. So I try to make a simplification here. Okay? Hello, go ahead.
Can you talk a bit about how you do the power loss resilience and if you still have it if you only have 2 sections?
Okay, so the main thing for the power loss thing is this garbage collection done AT, because the most critical path that is, when you lose information is if we were doing the garbage collection and something goes wrong, right? Because we're moving data from one sector to another. So if something goes wrong, that's where we're gonna lose data, right? Because for normal writes, like I said, we write the data first, and then the allocation table, the metadata. So data is valid once we finish writing the metadata. Okay. For garbage collection, when we start moving stuff, you will notice that we don't erase anything in the closed sector until we finish. Like I said here, the last step is that we write the garbage collection done, ATE, at the end, right? And then we erase it. So if something goes wrong, let's suppose that while copying these data, something goes wrong and we lose power. We started copying data, but actually we lost power. The next time that the system boots, it's gonna look for the open sector, but the next one is not erased. That's the first indication, and there is no garbage collection done ATE in the open sector. okay? Which means ZMS automatically understands that it needs to redo the garbage collection again. So that's how it doesn't lose the data on power loss. So it needs to do again the garbage collection, even if it partially it has been done before, but it needs to do it again, and then at the end, like I said, add the marker, which is the garbage collection done, meaning that everything is now has been copied. Okay?
Is ZMS also available in the native sim?
Yes, you can also simulate or use it with native sims. Yeah, it's already there. Sorry, I think he raised his hand before.
So say your next page is full, say you want to go to, and you try to garbage collect it, and there's nothing to do that effect, it's all still going to be valid. And that's the same for every single page. How do you prevent looping through the processing over and over again?
I don't understand. How do you prevent looping? That it should loop. I mean,
But say your flash is full.
Mhm.
So you've done right from your final page, you move on to the range page, you move on to the erase page,
Mhm.
and you copy from the next process, right?
Yes, I copy from here, for example, from sector 1 to sector 4. Okay?
But then in sector 1, all the data, none of the data was deleted previously, none of them had the flag deleted.
Mhm.
So you're like, that page you're writing now, sector 4, is full again. So you go to the next sector,
Mhm.
grab the next page, that's full. You keep doing that, because you have no more place to write. How do you prevent it looping through the whole process and making it so people?
So what you're describing here, that it's a full, the system is full, that's right? Okay, so when we do the garbage collection as many times as the number of sectors, which means that we loop all the sectors one time, all the partition one time, that means that the memory is full, and we exit, we cannot write that entry, and we report an error number. Okay, that's how is it done.
That's my question now. If we are targeting a system with a classic flash memory,
Mhm.
or in this case,
Mhm.
Nicolas doesn't support NOR, from what I know. But if we're targeting a system with NOR, why would someone use ZMS over Nicolas?
Um,
It's a little bit of an older question, but just can you give a few items maybe you have in mind?
like I said, ZMS is very scalable with the number of entry IDs that you can store, for example. So you have like 32-bit ID data. If your question is about the comparison with little FS, little FS is a full file system. Like I said, it's with trees, with paths, so it's slower for sure than ZMS. ZMS is a very direct way of storing data. Like I said, it's a key value storage system. So it's like every data that you store, you just put an ID, you maintain it in your application, and you store it. For people using, like I said in the slides, for people that sometimes they want to use path to store value, they use settings or maybe LittleFS, but it's slower for sure, because you need, basically what it does, it needs to maintain what's, the root path and all the keys that are stored in that root. So it's slower. This is faster.
It'd be nice to see some numbers.
Yes, I think.
Otherwise, you can just have a single directory structure, you throw everything in the root, right? And
Yes, but
how much slower it would
But with the NOR flash, it comes also with an overhead because also LittleFS needs to maintain the where leveling. It cannot write at the same location. Yeah, I know. But it comes to maintain the memory about where all the paths. It needs also an overhead. Okay. So, but I'm curious also about the numbers, if they are better or not. Okay.
I'm curious, I'm looking for like a script or scripts which can pre-populate like the flash before like compile the application.
Mhm.
I would like to generate a hex file which I then can flash on the device and which already contains some of the settings like based on ZMS and other NVS. started implementing it, but I'm curious if you know there's some implementations already. I haven't found any.
Current,
Generate all the structures.
yeah, you know, like a Python script that generates you the memory layout that is, I mean, with some entries that you want in. Currently, I don't know if such implementation exists, but
We have one downstream.
yeah, there is. Yeah, no.
It's internal, so but it's a very good idea. I think this could be a West command or something like to generate.
Yeah.
Could be made like
Mm.
Python.
Yeah, I know. In NCS, yeah, they have something that is downstream.
Good idea to have.
Where can I find something like that?
Yeah, in NCS, I'm sure there's something new.
Like a C implementation?
I don't remember if it's on C or Python.
It's Python.
It's Python, right?
Okay.
Okay. Any other questions? Okay. If everything is clear, then thank you for attending this session.